All right, so I got 11:15. A couple things I wanted to bring up before we get back into actual content. I've been getting a lot of questions over email lately, which is fine. I never want to dissuade you all from doing that. A couple things that I want to encourage you all to do in addition to that is, I'm guessing most of you this is your first time on campus, so maybe you don't know about the MCC upstairs. So if you need help with this class, you can always reach out to me, but there are lots of other resources. I just want to talk to you about a couple of them. So the MCC upstairs 303, they're open 9:30 to 3 in person, also 9:30 to 4 on Friday. They also have remote hours if you want to join them on Zoom, but that room is always staffed by at least one graduate math student, all of whom have been through Calc 1. So if you need help with this class, you can absolutely get help up there. Another thing I want to remind you of that I haven't seen really any activity on is so this is my view, but if you look at Canvas, maybe on the bottom view, you see this ed discussion. Basically, that's kind of like a message board where you can, if you have a question about anything, you can put it on there and I will see it and everybody in here will see it. And a couple of reasons I think that would be valuable if it got more use is, first of all, I get a lot of emails like after midnight, which is fine. I mean, you're not bothering me by any means, but I'm not going to see it until the next morning. So if you send me an email, really honestly, after 10, you're probably going to be waiting until the next day. Whereas if you use ed discussion or, in my experience, usually somebody has a Discord going for the class, if anybody wants to volunteer that information. But just more likely that you'll get heard right away and get an answer sooner. Also, I mean, it's probably been 20 years or so since I've learned the stuff I'm teaching you now. I'm not totally familiar with the things that you might be struggling with, but the other people in this room who are learning it along with you, they might have a perspective that'll be valuable to you that I might not be able to offer you. So again, I don't want to discourage anyone from reaching out to me. I'm always going to be a resource for you, but just take advantage of other things out there that'll be valuable as well. Any questions about either one of those things? Go ahead. The physical place, the MCC, the Math Community Center, that's in this building, room 303. It's pretty much directly over our heads. Just take the stairs up 2 flights and then it's like on the way out of the building. I'll be in there today from 2 to 4, but a few of you have mentioned that you're going to stop by. That's great. If you don't want to wait, you can go up there right after this class and somebody will be in there that you can talk to about Calc 1 stuff. All right, let's get back into it. We have a little bit left on section 2.1 to do. All right, so this table here, this shows the national debt from the year 1990 to the year 2010. And I believe the table, the right-hand column there shows the, I think that's in millions of dollars. So for example, in 1990, it was $3.2 trillion. In 2010, it was $13 trillion. So do a couple things with this. First, I want to estimate the average rate of change over that entire interval. So if I'm looking for, and the operative word here is an average rate of change, how am I going to find that? Let me draw a really, really rough graph of what's going on here. So from time 1990 to time 2010, and this is not going to be for accuracy or anything, I'm just doing it to kind of give myself a way to organize it. So basically, here's my point. It's going to give me national debt at 1990. Here's my point. It's going to give me the national debt in 2010. I want to find the average rate of change. Any idea? So the operative word there again is average. We talked about this a little bit last time. All of the Y values? I don't need all of them. So I kind of see what you're getting at, but I don't need all of these points. Right. So yeah, the average rate of change is going to come from, this thing we talked about a little bit last time to kind of motivate the derivatives. This is a secant line. So I'm going to pick 2 points on this curve. I'm going to join them with a straight line, and I'm going to find the slope of that straight line to find that average rate of change. So average rate of change is going to be equal to D of 2010 minus D of 1990 over 2010 minus 1990. So what do we got? 13,050.8 minus 3233.3 all over 20. If somebody gets to it before me, just shout it out. $6,340.75, and that'll be, I think, millions of dollars per year. So that's the average change over that interval, right? Is there any calculus that we needed to do there? All you really needed to do was find the slope of a straight line. So as opposed to, now I have swapped out the word average for the word instantaneous. So I want the instantaneous rate of change in 2000 as best I can estimate it. So anybody have any ideas how I can go after this? Like, this is a little strange because everything we did last time, finding derivatives, we had a definition of that function, right? I had an expression for you that we could use. So let's just remind ourselves of the notation. What I'm really after is this, d prime of 2000. And the reason I'm just going to have an estimate here is I only know what's happening in 5-year intervals, right? So I just looked at a 20-year interval. Now I can look at a 5-year interval, right? And there are a few ways to do this. They're all going to give you slightly different estimates, but probably the best way I can go at this is I'll just pick a 5-year interval. I'll pick the one that ends with 2000. Remember that derivative comes from a limit. I want to make my time values as small as I can. So right now, how wide is my time interval for what I'm trying to do here? 5 years. Can I do any better? Not really. I mean, if I wanted to do any better, I'd have to assume some things about what's happening between 1995 and 2000. But I can't really do that. I can't always get to an exact derivative. Sometimes I have to make some assumptions or take some shortcuts. Do you have a question? No, I mean, that was one way to do it. I could also, yeah, here's the good news and bad news. I already know I can't get to it exactly. So what I might do, I might take both of these. And unless a coincidence happens, these are probably not going to give me the same number, right? But what I might do, I might choose one, I might choose the other, I might average them both. But just it all depends on what data you're given and what you're able to do with it. If I had some nice definition for, like a polynomial, for example, what that expression did or how this function behaved, I would have much better resources. But this is about as well as I can do. Question? That's essentially what that is. I mean, I'm right. And so in this case, if I wanted to do it in terms of h, if I wanted to find the derivative around 2000, I could do this. The limit as h approaches 0 of which really, though, that is very similar to what's written above.
And is that like the simplest form you can get it in?
Yeah, but and the problem with this is, I have a pretty good idea of what to do when h equals 5, but then trying to pull in any closer than that, I don't really know what's going on. But yeah, they absolutely. I mean, we're still looking at that difference quotient. It's just how specific can I be about it? Good question. All right, and the last thing I want to look at here, just I mean, again, I'm not giving you an expression, but we can make estimates anyway. So I want to find the value of f prime of 3. So maybe we should unpack what that means first, just because we're sort of new to this. What does that notation mean, f prime of 3? So the derivative, all right, derivative. You said the derivative at the point 3. What's equal to 3 in that case? That's what I was getting at. Yeah, x equals 3, y equals 3, but even if you didn't say it, I believe we're after x equals 3, right? So derivative at x equals 3, or slope of tangent line at x equals 3. Again, this is not going to be exact, but if I were to draw a straight line here that was tangent to it, more or less, what do you think the slope is? I got to vote for 1. Anybody else? Yeah, it looks a little steeper than 1. 2 is about as well as we're going to do. Clearly positive, right? So clearly positive. Could I also say it's clearly more than 1? I think I can do that too. But again, you're kind of just looking, kind of eyeballing. But it's valuable to get a sense of, a derivative tells you how a function is changing over time, specifically at any given instant. So if you can kind of imagine, if you were to draw a slope at that place, draw a tangent line and find that slope, 2 is pretty reasonable. How about this next one? If I'm asking you, what does this mean? F prime of x equals 0. What is this notation telling us? Where is the slope of the curve 0? Or where is the slope of the curve equal to 0? Are there any points on here where that might be true? Give me one. I have a vote for x equals 1. Why? Okay. And you didn't say the word I was looking for, but you did gesture it. How would you describe this line, this tangent line here? Flat, slope 0, horizontal line, right? So yeah, if you were to draw any horizontal line, there's a slope of 0. So if you can kind of imagine where you have that slope of 0, where you're going to have that horizontal tangent, or if you want to be rigorous and talk about the calculus of it, the instantaneous rate of change there is 0. That function at that point is neither growing nor shrinking, it's not changing. So I got to vote for x equals 1. Are there others? X equals 4. Anything else? I think that's complete. As far as we know, just those two places. Any questions there? All right, you're done with 2.1. So on to 2.2. So 2.1, we talked about how to take the derivative of a function. And we talked a little bit about what that derivative is, but now we're going to get into a little more detail. If we haven't been explicit about it, or maybe you suspected this, maybe you haven't, but the derivative of a function is in itself a function. It's definitely related to that original function in some way, but it's a function in and of itself. So let's talk about this. So I'm giving you a graph here of a function f in blue. And from that graph, I want to create a graph for another function, f prime. So basically, I want to graph the derivative based on this function here. So I'm going to go ahead and get started. I'll start with, and make sure that maybe I'll check with you all. Anybody have any ideas how we can get started? Basically, is there a point I could say is definitely on the derivative right now? Go ahead. Okay, I think that's a good place to go. So here's a place where the slope is 0. I believe f prime of x equals 0. So then if I want to start plotting points for the graph of f prime, where should I plot a point? There you go. So on the x-axis will be a point there. And for the same reason, there's going to be a point here, I think. Point here. Do I have any other points that are going to be on the x-axis based on what I have? I think that should be complete. Remember, the blue graph is going to be f of x. This red graph is eventually going to be f prime of x. It's going to be the derivative of f. So if one of the ways we think about the derivative is the slope of a tangent drawn to that curve, or the slope of the curve itself, then any of these places where I can imagine horizontal tangents, and I'm going to erase these shortly, but I just want to illustrate what's going on here. These 3 points here, if I were to draw a tangent line, they'd be horizontal. A horizontal line has a slope of 0, which means the derivative is going to have a value of 0 at those 3 places. And I don't believe there are any other points that are going to fit that criteria for this graph. So now that let's look at these first 2 points on the x-axis. What's the derivative going to be doing between those 2 points? Okay. Let me ask this question. Is the derivative going to be positive between those points, negative between them, or some mix between them? I got 1 vote for only positive. I got another vote for only positive. How come? Right. So, yeah, right. So yeah, at the ends, the slope is 0, but in between them, I'll give you a couple ways to look at this. The function is strictly increasing between those 2 points, right? There's no point where it's decreasing, it's only increasing. Also, pick any point you want in between there and draw a tangent line. What's that tangent line going to have a slope of? Not necessarily 1, but what could you say about it? It's going to be positive, right? So I think I can do something like this, right? Yeah. How about between the next 2 points? What's the slope, or what's the derivative going to be doing? Negative. Should I make it steeper than this last bit I drew, or I think it should be, yeah. And then how about to the right of that point? Going to be only positive, and looks like it's going to be getting steeper and steeper. Final thing we should do is what's going to happen to the left of my first point there. Why do we know it's going to be negative? Right. So if you were to draw a tangent line anywhere on this curve to the left of that point, you know, it's going to be, the steepness is going to change. The magnitude of those slopes is going to be different, but I think they're going to be exclusively negative. So I don't want to rush through this. If there are any questions about how we constructed this sketch, now is a perfect time to ask them. Go ahead. Yeah, those are, and that's really the whole reason I wanted to do this, to show you how so the function in itself is a derivative, and it has a very, very explicit relationship to the function it came from. And we're not going to do it right now, but I could very well ask you to graph f double prime, which would be the derivative of the red graph. So I mean, most functions you can just take derivatives of infinitely. Go through it. I said yes. Something that. So I don't know if now is the right time to jump into that. Anything else about this? Okay. So this is something we've done pretty recently. I am giving you this function. I want to find a formula for f prime of x. So I want to find a derivative. How do we do that on Wednesday? Sorry, what was that? Yep, we're looking at this difference quotient again. This time I'm just going to call it x plus h. I think we used the a last time. Let's just keep the variable. f of x plus h is going to be x plus h cubed minus x plus h minus x cubed minus x. Didn't put the limiter in there. I'm going to fast forward a little bit because I think I can. But if anybody has any questions about what I'm doing or why I'm doing it, please stop me. Please double check that. I feel really suspicious of it. All right, what cancels? Looks like the x cubes cancel, the x's cancel, and I am left with 3x squared h plus 3xh squared plus h cubed minus h. All right, let me stop there. You agree with me so far? And we're getting to a place where I can evaluate this limit because I can factor out an h in the numerator and be left with 3x squared plus 3xh plus h squared minus 1. So what is the derivative then? 3x squared minus 1. Any questions on how we got there? A little bit what? Yeah, I'm going to guess that the most mysterious thing that might have happened here is me expanding that cube. That's more or less, I mean, that's something I kind of have just remembered from doing it over and over again. But if you want, I would ask you to do this kind of independently, convince yourself that if you were to actually expand all those things out, you would get. And just to kind of give you a concrete example of what we just did, I just gave you a random graph and we sketched this derivative. Now that I actually have a function, I can do the same thing here. So I did this in Desmos. Here, the red graph is y equals x cubed minus x. And the blue graph is y prime equals 3x squared minus 1. So if you compare where those points on the red graph where the slope would be equal to 0, see how that corresponds to what the blue graph does. If you look at the points on the function on the red graph where the slope is positive, look at what implication that has on the derivative. Things like that. Just for one example here, over here, what can be said of my slopes in this region here, in this neighborhood? The slopes? Positive. So yeah, the values are negative, but the slopes are, this function is increasing. So what does that mean my derivative needs to be doing? Needs to be positive, right? But yeah, lots of connections you can make there. But basically, you can all the relationships you'll see there are kind of what we built up in that first slide. Any questions so far? All right, I want to find a formula for f prime of x, given this weird function, the radical x. X equals 0, h to 0. So I'll go ahead and get it started, and then I'll stop if we get stuck. So the square root of x plus h minus the square root of x over h. From here, how might I keep going? We'll talk about the conjugate. Yep, I got radicals. See if I can clear them that way. So radical x plus h minus radical x all over h. And I want to multiply by radical x plus h plus radical x. That should clear the radicals in the numerator, so I'll have x plus h minus x over h times all these radicals. X plus h. I'll pause there because I think I might have gone a little fast there, but I'll pause for questions. We okay with what I've done so far? Those of you who have kind of been through the power rule stuff and seen this derivative before, does it look like what you expect? So can I evaluate this limit now? So this becomes 1 over 2 radical x. How do I get from the third step?
Yeah.
So from this one to this one? So the x's cancel, right?
Oh, wait, okay,
Yeah. I took a little bit of a shortcut with the conjugate because just to kind of remind you, the whole reason of doing the conjugate or some multiplying by a conjugate is so that my middle terms will disappear. So knowing that that's the purpose for doing it, I just ignore that step. So radical x plus h times radical x plus h, that becomes x plus h. And if you were to take the middle terms here, all right, now let's use this thing. Now that we have it, we can use it. I think I'm going to skip this one for now. I'll leave this as a exercise for you all. I believe that it's something you could do, but I think it will take us a lot of time to develop here. But if the difference quotient is not something you feel totally comfortable with, I think this is a good one to get from Canvas later and give a shot. So, a little bit of historical context. Calculus is one of those things that it was basically being developed by two different people at the same time and independent of each other. The ideas are all basically the same, but a lot of the notation that got used between them was different, but it's all more or less become standard. So I wanted to give you explicitly some different flavors of the notation, much of which I've already shown you, but I just want to collect it all here. So if y is some function of x, f of x, a lot of these things you'll see here are equivalent ideas, but maybe say those things in different ways. So long string of equalities here, but we already talked about anything with y prime. Something I don't think we've done a ton of yet is this liveness notation, where we use this ddx operator. So basically, in this context, I'll unpack these a little more because I think they need it. That lowercase d there doesn't really mean anything on its own. What it means is it's basically the rate of change. So dy dx, really what it's implying is, what's the rate of change of y with respect to x? What's the rate of change of y with respect to some small change in x? And by that same token, the next one, what's the rate of change of f of x with respect to changes in x? One thing I will say is this ddx right here, a lot of the times you'll see this as an operator, and it just means to take the derivative of whatever's sitting to its right. And just to kind of get ahead of some confusion that I've seen in the past, this ddx right here, it's kind of useless on its own. A good analogy I have for it is, what does this mean? Square root, right? But if I don't put something on the inside of it, it's meaningless, right? So ddx is much the same way. I mean, it means I'm going to find the derivative of something, but you need to unpack what that is, or you need to specify what that is. Oh, sorry. So the first, that middle bullet there was really all about, the derivative as a function. I'm not interested in any one singular point yet. I'm just interested in what's going on with that function. If, on the other hand, I'm interested in a specific point, you'll see this Leibniz notation here, and I keep using this name. So this is Leibniz notation, basically anything that involves the ddx operator. Your question? I think you'll probably see any or all of these in the textbook, on web work in the future. So I wanted to make you aware of them. But if you need to be reminded, definitely let me know. Any questions about any of this notation stuff? All right. So let's talk about the idea of differentiability. So those of you who looked at the quiz, I think this is the last question on there, is talking about if a function is differentiable. What does that mean? And here is the, it sounds simple, but there's a lot of implied stuff on here. A function f is differentiable at a if f prime of a exists. So if f prime of a exists, what does f prime of a mean? Slope of the point? Or slope? Not slope of the point. Slope at that point, right? So why might the slope at a point not exist? So if the function is not even defined there, it might not even be continuous there. And if it's not continuous, it can't be differentiable. That's one of the ways. There are other ways, and we'll see some examples shortly, but it's a very simplistic kind of statement here, but there's a lot to unpack, or there's a lot that's kind of implied here. So we need f prime of a to exist. In all the ways we've calculated derivatives so far, what's our only understanding of f prime of a so far? How do we calculate it? Basically, it's the limit of this difference quotient, right? So if f prime of a exists, what can you say about this limit? The limit exists. So really, the idea of differentiability is substantially no different than you trying to find out whether a limit exists or not. It's just a very specific limit, the one that defines the derivative. Any questions here? We look at maybe one example, maybe two. Okay, so let's look at a function here. F prime of x equals absolute value of x. And I think many of you probably have a picture in mind of what this looks like. Where is this function differentiable? We got to vote for everywhere. Anybody else? I got to vote for everywhere but 0. So let's think about it. Let's break it up into at least 2 sections. Let's say I only want to look at positive values, and I only want to look at, x equals 0. And really I care about points, so let's do this one first. Let's f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h. Think about the way this function behaves on the right-hand side of the y-axis and the left-hand side of the y-axis. If I were to break this up in half, what is this function here? What was that? It's positive. We can be more specific than that. It's linear. We can be even more specific than that. I should be able to come up with an equation for this, right? Yeah, what's the absolute value of 1? What's the absolute value of 10? What's the absolute value of 30? You're describing this line, right? No matter what the x, so as long as x is positive, and just to kind of show you how how it behaves over here. What's the absolute value of -2? What's the absolute value of -9? I got you.
Yeah.
So what is this line over here? What did you do to all the x values that I gave you? Yeah, you made them positive by taking the opposite of them, right? So really that's another way to think about it. For all negative values, and it's y equals x for all. So knowing that now we can talk about this limit a little more. The limit as h approaches 0 of f of a plus h is x plus h minus f of a, which is, oh, not x, minus a over h. So that limit is just going to be 1. Which, if you think of what a derivative means, hopefully that's not surprising. If the derivative is a slope of a tangent line, and the thing on the right just is a straight line, that means it has the same slope everywhere, right? So that derivative is 1. So I'm going to put a check mark here. If I have a strictly positive value of a, my function is differentiable. We're not going to go through it, but by the same logic, if I have a strictly negative value of a, it's going to be differentiable. The derivative is going to be -1. But what happens if a is equal to 0? So f prime of 0 is equal to the limit as h approaches 0 of f of 0 plus h minus f of 0 over h. Just the limit as h approaches 0 of h minus 0 over h, which looks like it's going to be 1 again, right? But we're looking at a two-sided limit here. What is h going to be equal to? I mean, on the right-hand side, like, let's say I'm approaching from the right. In fact, we should probably do this. Let's just look at the right-hand limit. What is the limit as h approaches 0 from the right? It's just going to be 1, right? Because h is going to be a positive number, f of h will just be h. That limit will be 1. But let's say I approach 0 from the left. The f of h over h, right? But if h is negative, what is f of h? Yeah, it's. I'll go a little further here. So the limit is h approaches 0 from the right, 1. Limit is h approaches 0 from the left is -1. What's the limit of h? Does not exist. So the limit as h approaches 0 of f of x does not exist, which means f prime of 0 does not exist. And as you're packing up one more way, I'll give you just to kind of those of you. If you were to draw me a tangent line at x equals 0, it's hard to say, but I can draw a tangent line. Is not. About that definition, but there is a reason that tangent line rationale falls apart too. Yeah, it needs to be unique. Right. So, and I'll say this again. That's pretty hand wavy. It's not very convincing. Really, the bottom line is, does that limit exist that we just went through? In this case, it does not. All right.